Hello everyone, welcome to an algebra tutorial video learning about exponential decay but applying it to population growth. So here's our problem that we're going to be looking at. The current population of Japan is about 127 million, but the growth rate is a negative value. It's a negative 0.2%. And these numbers are from just doing a quick Google search. What will the population be in 10 years? That's our problem here, is trying to model and think about population and the change that happens. Population change happens often on an exponential decay. So we're given a percentage, and that percentage change happens every year. So let's think about what these numbers mean. We know exponential functions always fit the form f of x equals a times b to the x power. So we need to translate this problem into that math language, into an exponential function. So I need to find value for a. Remember, a is my starting value. So my value for a in this problem is going to be 127 million. So I'm just going to put that in there. A equals 127 million. 1, 2, 3, 4, 5, 6. That's my starting amount of population. All right. My growth rate is negative 0.2%. So how do I translate that into b, what I'm multiplying by? So what that means, if you remember in exponential decay, that happens when we multiply by a number less than 1. B has to be between 0 and 1. So when I'm given my growth rate is negative 0.2%, I can interpret that to mean I'm starting at 1. 1 means I'm multiplying by the same thing and staying the same, but I'm decreasing, and I need to translate negative 0.2% and to translate that into its decimal equivalent, which is negative 0.002. We divide by 100, right? 0.2%, 0.2 per 100. So I take that, divide by 100, and this is the decimal that I want to use. So I have 1 is what I multiply to stay the same, but I'm declining. My growth rate is decreasing, so it changes by this 0.0002, and that's going to be my value for b right there. If I do some simplification, it ends up just becoming b is 0.998. That's what I get when I take 1 minus the 0.002. All right, so there's my starting value, there's my constant multiplier, and I want to know what will the population be in 10 years, which means I'm going to multiply this 10 times, or I'm going to input 10 in for x, take it to the 10th power. So let's go ahead and calculate that out now. So I'm going to take my function, I'm going to write out the function, and then we'll calculate out. So in my function, I'm going to input 10 in for x. I want to know after 10 years, my starting value is 127 million. I'm multiplying it by 0.998. So we have exponential decay. That's a number smaller than 1. I'm taking it to the 10th power because I want to know in 10 years from now. So there we go. We got some direct meaning from my function based off the problem. And if I calculate that all out, my calculator, so will give me some interesting things, at least for mine. I want to make sure you're understanding too. So it initially gives me 1.24483, and it's got this little e down here, and then an 8. And just so that doesn't trip you up, all that e means is it's a calculator's way of doing scientific notation. It means the same thing as 1.24483 times 10 to the 8th. There's scientific notation. So that e means just times 10. But if we wanted to write it out in standard form, that's just 124 million. I can just multiply it all out. 483,000. So there we go. We can see that if the population of Japan currently is 127 million, but their growth rate is a negative 0.2%, they're going to be declining by about 2.5 million over the next 10 years. There's going to be less of a population. That's a real concern that the Japanese government has to think about in terms of taxes, in terms of kids attending school, in terms of the number of people that need services. They're facing a serious concern because they don't need as many services. They're going to be declining in things. So you can definitely tell this is a very important application of exponential modeling and exponential functions to be able to predict, plan ahead, and think about what's happening with population change. Now I've also got this thing pulled up for you. Give me a second, I'll pull up the table and the graph, and we can just look at some other things and make more sense of this mathematically. All right, here we are. So you can see we got on the left side a table of values. So I can see for increasing years over the 10-year change. What happens in my years? I see that we have some exponential decay. We're declining, right? So my table of values, I can see for every year a slight decrease, down and down, following my exponential model. And then we also have a graphical view. There's my starting value right here. In 0 years, we had 1.27 or 127 million. But then it's also showing exponential decay down here. And there's after 10 years. So if you're doing math, a calculation like what we did is nice, but use a graph or a table. In this case, I used the online desmos.com calculator. It's a great one. You can just put in the function and easily pull up the graph and plot these values and tables, etc. But it helps justify, it helps make sense that we did the problem correctly and helps us support what we do. We can even use it to find other values as well. What if I only wanted to find the population in 5 years? So we got that value right there as well. Now it looks like a straight line because we're multiplying by a value so close to 1 that the change isn't that great. And so even though there is a slight change, and even though I could show it's exponential by dividing all these, it almost looks linear because it is such a small amount of change from year to year to year. Sometimes, we've looked at exponential decay before and we're expecting to see kind of a graph that looks curved a little bit more like that. It doesn't necessarily always have to be like that. This is an example of exponential decay.